Heat capacity and specific heat, part 2. If you have not already watched part 1, you should really go do that. Heat capacity for any object depends primarily on two things. It depends on the mass of the object and depends on the material the object is made of. For example, here we have two mineral samples. If someone asked me to compare the heat capacities of these two separate objects, I would have a hard time doing that because they have different masses. This one on the left is a little heavier, and they're made of different materials. This is sulfur right here, whereas this is pyrite, which is a mineral made of sulfur and iron. So let's try to make the problem a little simpler. Let's bring in a second sample of pyrite. Which of these two has the greater heat capacity? You ought to be able to reason this one out. The larger sample has the greater heat capacity. Now, how do I know that? Well, it takes a certain number of joules to raise the temperature of this sample right here by 1 degree Kelvin. I know that it's going to take more joules to raise this by the same 1 degree Kelvin because, hey, if I were to cut this into two pieces, say this was twice the mass of this over here. It might be a little more than that. Let's say it's twice the mass. If we cut this into two pieces, each one of those two halves would have a heat capacity equal to this because it would have the same mass. So if you put the two pieces together, however many joules you need to raise this by 1 degree, you need twice as many joules here. So clearly the heat capacity of this is greater. If this was 3 times the mass of this, you could cut it into 3 pieces, and each piece individually would have the same heat capacity as this, and altogether this would have 3 times the heat capacity of that. So the heat capacity is actually directly proportional to the mass. Whatever ratio you have between these two masses, it's probably not exactly 2 or 3. Maybe this is 2.7 times whatever that mass is, and that's what the ratios would be. So that's nice that we can say something intelligent about these. It would be nice if we could go one step further and come up with an actual number for the heat capacity. How might we do that? Well, the hard way would be to actually take one of these samples and do an experiment where we literally heat it up and measure the temperature. Now, that's not easy to do. Measuring the flow of heat directly is notoriously difficult. What would really be nice is if someone else had done the experiment for us. Maybe if someone were to measure the heat capacity of some reference mass, maybe like a 1 kilogram mass, if we knew what that was, then we would know that these heat capacities here would just be proportional to whatever that was. If this was, say, half a kilogram, then this would have half the heat capacity of the 1 kilogram, and so on. The good news is someone has done that experiment for us. We can look up what the number is for the heat capacity of a 1 kilogram sample, and in fact, that's just what specific heat is. Specific heat is just defined as the heat capacity for a 1 kilogram sample of whatever material you're talking about. When we know the heat capacity of some specific standard mass, could be a kilogram, could be a gram, we call that specific heat. There it is. Specific heat is simply the heat capacity of a certain mass. I suppose it's specific in the sense that we specify the mass. Could be kilograms, could be grams. Chemistry people tend to prefer grams. Physics people tend to prefer kilograms. The specific heat and the heat capacity of an object is actually the same number if you're talking about a 1 kilogram object. If the object is not 1 kilogram, you can calculate the specific heat because that's just the heat capacity per kilogram. It's just the heat capacity divided by the mass, and there are the units, joules divided by kilograms times degree kelvins. Joules per Kelvin are the units for heat capacity, and then if you divide by kilograms, you're going to get those units right there. For example, pyrite has a specific heat of 518 joules per kilogram degree Kelvin. If this sample was, say, half a kilogram, which I think it might roughly be a half a kilogram, then the heat capacity of this sample would just be half of whatever that number is. So half a kilogram would have a heat capacity of 259 joules per degree Kelvin. Now, calculating all this can be confusing, so we'd like to have a formula. Let's take a look at the units just like before. Energy equals specific heat times mass times change in temperature, and that suggests a formula that looks like that. This is just the same thing we had before. There's Q for the heat energy, there's delta T for the change in temperature. Now let's compare this to the formula we had before for heat capacity. So here they are side by side, and you can see that there's yet another unnecessarily confusing aspect of all of this, and that's that they like to use the same letter, C, to represent two different things, heat capacity and specific heat. Generally, they use a uppercase C for heat capacity and a lowercase c for specific heat, and you just need to get used to that. But you can see that heat capacity equals specific heat times mass, and therefore these two formulas are really one and the same. So when people are being sloppy about this terminology, heat capacity, specific heat capacity, you just have to remember that specific heat and specific heat capacity have the mass units. And there's the mass variable right there in the formula. Whereas heat capacity has no mass units, neither there nor there.